A measurable effect of temperature on materials is expansion. In other words, as the temperature increases, an object actually increases in size. In other words, it expands. I have three formulas here on the key concept slide. The first one is for length expansion. So this is maybe the foundation of the other two formulas, it turns out. But if I had like an object like maybe a rod or something like that, something that is maybe thin and long, in other words, this would probably be the appropriate formula. If I wanted to calculate, well, let's say for a temperature change, what is its increase or possibly decrease in length going to be? If the temperature goes down, whatever object it is going to decrease in length. So if it's like, let's say, a steel rod or something like that. The one thing I would need to look up, though, is this alpha symbol right here is the coefficient of expansion. So I would need to look up the coefficient of expansion for steel. I would need to know the length of the rod, though. So an interesting ramification of this formula is one of the inputs is the length that is already, in a sense, there, or that really is the length at whatever starting temperature of that rod. In other words, if you ask, like, well, let's say I've got like a 10-foot rod and a 20-foot rod, and then I say the temperature increases by, say, 10 degrees Celsius. Might seem weird that I was mixing unit systems there, but anyways, if I did that and I asked, well, so is the amount by which those two rods going to increase in length going to be the same? The answer is no. The longer rod will increase by a larger amount, and in fact, it's proportional to how long it already is. So if it's a 20-foot versus 10-foot, the 20-foot rod will increase in length by twice as much as a 10-foot rod for the same temperature change. The area formula has this extra 2 in it, but it's basically change in area is equal to 2 times coefficient of expansion times the area that the object has before it expands, you could say, times the temperature change. One way of thinking about why this 2 might make sense is that when you have an area that is expanding, it's kind of expanding in 2 dimensions. So if you base that off of the same coefficient of expansion, then simply multiply by 2. I have seen some texts present this slightly differently, where they will use a new symbol for an area coefficient of expansion, and then they'll simply say that the area coefficient of expansion is always double what the linear coefficient of expansion is. But I feel like that's introducing unnecessary symbols when you can just put this 2 in the formula and use the same expansion coefficient for any of these. So just be aware, if you look at other sources, sometimes this is presented a little bit differently. And similarly for volume, since there's 3 dimensions for it to expand in, now there is a 3. It depends on how much volume the object occupies to begin with. And of course, it depends on the temperature change that we're considering that leads to that expansion. Or of course, if it is a cooling, cool down type of situation, then I would model delta T as negative. And that would mean that the object actually shrank because the delta V, the change in volume, would be correspondingly negative.